So here's a glomerulus, and we've talked about how fluid coming through here gets squeezed out through these capillaries of the glomerulus, and that fluid goes into this cup-like structure that we call Bowman's capsule. So it gets collected here in the capsule and sent down into the nephron. Now the amount of fluid that gets squeezed out through all of the glomeruli of both kidneys is called the glomerular filtration rate, GFR. And in this video, let's talk about what determines this GFR, what makes it bigger, what makes it smaller. So the way that fluid gets out, as we've said, is it gets squeezed through these little holes in this capillary. So one thing that'll clearly make more fluid come out of these holes is if you raise the pressure in these capillaries. If you squeeze down on them really hard, then you're going to shoot more fluid out of these little holes than you otherwise would. So capillary pressure is going to increase GFR. And actually, this is one of the reasons why these glomerular capillaries have much higher pressure than other capillaries in the body. So their pressure is usually about maybe 60 millimeters of mercury, whereas other capillary beds have a pressure of 20 to 30. But at the same time, since pressure in the capillaries would push more fluid out, then pressure in Bowman's space, pressure out here, would make it harder for fluid to come out of these holes. So capillary pressure increases GFR, but Bowman's space pressure would decrease GFR. So these are two important factors, but there's actually one more that we need to consider. And that has to do with the idea of osmotic pressure. So let's go over that quickly. The idea of osmotic pressure is that if we have some membrane separating two bodies of fluid, and if that membrane is permeable to the water, but not to solutes in the water, so let's draw some solutes. So if that's the situation, then what happens is water tends to get dragged to the side with more solutes. And you can think of that almost as a kind of pressure that pulls the water over to the side with solutes. So we can actually think of the capillary wall as this kind of membrane, because the capillary wall is permeable to water, but the capillary wall is not permeable to some solutes. And you might be confused because we said that all the solutes like sodium, potassium, glucose, amino acids all get out easily of the capillary. Well, they do, but there's one solute that doesn't, and that is proteins. As we mentioned, proteins cannot get out of the capillary into Bowman's space, and proteins are a solute, and they do cause a kind of osmotic pressure. In this case, instead of electrolytes on this side, we have proteins. And so in that case, this would be the capillary side, and this would be like Bowman's space. And so because of these proteins over here in the capillary, water and actually all the other things that can cross, including those electrolytes, get sucked back into the capillary. So the presence of protein over here in the capillary, we can say capillary protein, actually reduces GFR because it drags fluid back into the capillaries from Bowman's space. Now, one thing to mention is that this dragging of water by proteins is actually usually not referred to as osmotic pressure, it's referred to as oncotic pressure. And the difference is that proteins are a lot bigger than electrolytes, and that ends up causing the fact that the pressure that they put on this water, the amount that they drag the water is actually more than the amount that electrolytes are dragging. So it's a little different, and so we call it oncotic rather than osmotic. But it's exactly the same principle that causes it. So this leads us to the equation for GFR, which is that GFR is equal to some constant times the pressure in the glomerular capillaries minus the pressure in Bowman's space minus the oncotic pressure from the glomerular capillaries. And then technically we add this term plus the oncotic pressure of Bowman's space. And the reason we add that is that Technically, if you had proteins out here in Bowman space, they would drag more fluid into Bowman space and increase your GFR, but normally you don't, you shouldn't, so normally this term would be 0. Now what is this little constant here, this Kf? Well, this contains all the other factors that would be important. Mainly this tells you kind of how much total capillary surface area you have. So if you had more glomeruli, you would have more total capillary surface area. So if you had, for example, twice as many glomeruli, this constant would get twice as big because you would expect that GFR would be twice as big. With twice as many glomeruli, you would filter twice as much fluid.